there's any questions, you might use the raise hand functionality that we've got in Teams. And if I see that and Professor Martinez doesn't see it, then I will try to notify him as gentle as possible to interrupt as little as I can. And then secondly, also for you, for Professor Martinez, is if you have the need for a break because you might be speaking a lot, then please feel free to indicate so that we have a 5 or 10 minute break at any given time that you think you need it.
Yeah. Okay. Okay. Yeah, let's say I have, don't know exactly how many slides, but my target is at least 90 minutes. And I think I can do it in one shot. So that's, let's see if it's.
There's a few extra people joining the meeting. There's Jacques Wheeler from CPT. Welcome to you, Jacques. And then there is another, I think a student, is it possibly from Nelson Mandela University? Somebody I do not know, but warm welcome to you as well. Which means that we are presently with 11, including myself. So also for the late arrivals, if you've got any questions, then you can either use the raise hands functionality or gently interrupt Professor Martinez somewhere in his presentation. He's happy with that. If there is any other thing that you would like to point out to me, please use the chat functionality. The meeting is being recorded so that you can review it at a later stage if you want to, if you need to. And I aim to distribute the recordings later this afternoon. But apart from that, I do not have any other further introductions. Annick, maybe you have something that you would like to add in this?
Not specifically, but I would like to ask Wilmar to introduce himself and especially explain the experience he has. He worked over the whole world, I think. You were in Japan, in Colombia, in Switzerland, in Finland, and so on. We are people who are interested in practical issues too, in details too. I explained it to you. So please introduce yourself and say what your experiences are and also which research you involved in or initiate. Thank you.
Yeah. Okay. Yeah, first of all, the questions of every online meeting. Do you hear me well? Do you hear any echo?
Yes, it's very good.
Or...
Yes, loud and clear.
Perfect. Good. So, well, first of all, thanks for the invitation to present this amazing topic. Yeah, let's say I can introduce myself. I have prepared some slides, one slide about that. Yeah, Wilmar Martinez. I am originally from Colombia in South America, and now you were mentioning these issues in South Africa. I would say that is quite similar also in South America. We have a lot of water and we produce a lot of electricity, but still a big part of the country is not connected to the main grid, or is quite decentralized. And we face also quite a lot of issues where microgrids are actually one of the possible answers. So did my education in Colombia, then as Annick was mentioning, I moved to Japan to do my PhD in power electronics, and more specifically in electric cars. I started my journey with electric cars in 2009, perhaps. And then during my stay in Japan, we had a quite good connection with the manufacturers or the OEMs in Japan, and therefore we started to work in the powertrains of hybrid electric cars at that moment. So that was actually the topic of my PhD. Sorry. Then I moved to Toyota, also in Japan, and there I was working also in powertrains, but more closely to the electric motors, working in magnetic materials and effects on power conversion in machines. Then we decided to move to Europe, and I was a postdoc in Aalto University in Finland, and there the research was a little bit different, but still in the area of power electronics and more oriented to the semiconductors. Lately, I visited ETH in Zurich, and I worked basically in how to optimize power converters in general, but with certain applications also in electromobility. And since March 2018, I joined KU Leuven and Energieville as an assistant professor, and currently I am co-head of the power electronics team, dealing with a wide variety of topics within the area of power electronics, but most of them intended to be applied in electromobility, as we will see today, and also renewable energies and DC grids, as George already presented 2 weeks ago, I believe. So that's my journey basically, and how I ended up in working in Leuven and at Energieville. So basically what I wanted to present to you today is first a few slides about our group. I know that George presented quite well the activities of Energieville, but still some sub-activities in the area of power electronics. I think that can be further explained, and then I will jump directly to the EV chargers. Same as power electronics. Power electronics is a big word dealing with a wide variety of disciplines. Electromobility itself is the same. It's quite difficult to put everything about only one topic in 90 minutes, and it's the same regarding EV charging and infrastructure and technologies around it. So I will do my best to cover it. But still, as it was mentioned in the beginning, the recording will be there, and if you have much more to discuss, you're welcome to contact us and yeah, continue the discussion. Infrastructure, a little bit about infrastructure regarding EV charging or battery charging in general, because it's not what I will explain is not only related to cars, but now more and more we will have batteries at home, so it's also applicable to that. Trends and impacts. I think if we are talking about electric cars, immediately many people think on the impact on the grid, basically, that we will have if we really have a large penetration of electric vehicles in our cities, in our countries. And finally, some conclusions. So one acknowledgement, of course, to Camilo Suarez. He's one of our PhD researchers in our group working in EV chargers, and some of the slides were made by him, so an acknowledgement to him. So let me start with the power electronics and at Energieville. Once again, George presented quite well what Energieville is. And just once again, the invitation to all of you to go and check our tours out. Basically, we have also a YouTube channel. Yeah, and you can check those. I think there's quite interesting material about the facilities and how Energieville works. By the way, this week we are having our, let's say, is a celebration to Energieville, because we got our 10th birthday, and yeah, you can also check the information about this jubilee at Energieville. But something that I want to add is that more and more we are talking about energy transition, and this is one of the let's say, photos or pictures that I like the most in terms of energy transition, and is how let's say an area or a place that was dedicated for coal mining was translated into certain research institutes or research collaborations towards topics around energy. You can see this building is the Torre Central. It's exactly the same building. I think is already more than 100 years old. And there is exactly one of the examples of how energy transition can play an important role in our society. But yeah, that's basically what I wanted to say, or to complement the part that George mentioned 2 weeks ago. Now I will land in the power electronics group. In the power electronics group, we have basically 2 activities: the low voltage DC grids that were explained by George in detail, and also the power converter activities, quite hardware oriented in our group, and also quite complementary to the low voltage DC activities. So what we do, well, perhaps a little bit of advertisement from our side. This is some of the activities that we are doing, the international outreach. We are part of the Power Electronics Associations in Europe, Power Supply Manufacturer Associations, also members of a wide variety of associations in regarding power electronics and modeling. We do hardware, at least in activity that I mentioned regarding power converters, and some of them are actually for electric vehicle charging. We do have projects like the ones that George mentioned before, not only in the low voltage DC side, but also in the power converter side. And yeah, we have a wide variety of connection with industry. As you can see here some examples. Within the power electronics activities, our main focus is not only dedicated to that, but our main focus is low voltage applications, so lower than 1.5 kilovolts. Still, we have some activities with modular multi-level converters that can reach higher voltages, but that's, let's say, less than the 10% of our activities. Within this area, we try to optimize, and we try to create solutions in power conversion that can offer advantages in what we call a combined performance, meaning that it's not only thinking, for instance, in a electric vehicle charger, not a charger that is efficient, but also that is cost effective, that is that offers a small size and so on, that we can tackle different, let's say, objectives at the same time. How we do that? We go to the component level at Energy Build. We have material and component development at the level of batteries, semiconductors, and solar panels. And there we use that knowledge also combined with the knowledge of for instance, in passive components, in magnetics, from my background, for example, and also the parts of the semiconductors. We do modeling also. We go a little bit down in that scale to the what we call a multi-domain or a multi-layer or even multi-physics domain, where we model the interaction between, for instance, the magnetics, windings, noise, temperature, and so on. So that's basically our approach. But at the end, once again, the idea is to have an improved performance in our power conversion systems. So that's the activities. Regarding electromobility, or specifically electric vehicle chargers or battery chargers, I can show you 3 examples of projects. These are 2 complete projects and 1 ongoing project. But The first one is this SmartOR data platform. It's already a project that already concludes, but still there are some let's say activities that were derived from this project in the topic of smart charging. And as we will see in the presentation, in my opinion, this is one of the keys to let's say to tackle several challenges that the great adoption of electric vehicles will raise in the coming years and decades. And basically, yeah, we will have, like in our case at EnergyVille, the project was intended to expand the number of charging points in the building, and also now it will be even expanded further with the expansion that George told you in the lab. So we will have more points. But at that point it was initially 7 charging points, and the project was to expand up to 25 charging points. Low power, I would say. There is a fast charger also in the building, but these ones were low power. And the idea was, of course, to integrate let's say the renewable energy generation that we have in the building, and more than that, to obtain data out of these charging examples that we have. The building counts with some electric cars, but also part of the staff also is riding electric cars. So that was a good chance to get data and analyze how charging is performed actually in that living lab that EnergyVille is. But as I will tell you later, perhaps at the very end of the presentation, the key was the smart charging. The challenge is not that our current grid will not handle the amount of cars that we will have in the future. The problem will be the peak that will be generated when we connect many cars at the same time. And that was exactly the same happening at EnergyVille. Everyone comes in the morning, 8, 9, or 10 a.m., and they directly plug their cars in. And there is indeed a peak that is generated. So basically, it's of course not that difficult, but it's basically to delay certain charging processes during the day. That was basically the idea of this smart charging. But I will give you some other details about it later. There was also a project. Someone mention anything? No. There was also a project in terms of not the charger, but more in the car towards a powertrain and how, let's say, an inverter intended to be used in a motor drive. It was a 100 kilowatt inverter could the operation in the terms of the cooling needs that certain use of specific semiconductors and materials can raise. That was one case. And finally, this is the project that we are conducting at the moment is one module of a fast charger intended to be used in a 350 kilowatt fast charger. And the optimization of that charger towards a wide variety. I will tell this in detail. A wide variety of cars and conditions that we can have for a charger. This one I will explain it more in detail. So these are some examples of ongoing and past activities that we have in the group. In the topic of electromobility. It's not only limited to this, but perhaps relevant for the discussions that we will have, or that I will present in the coming minutes. So let's jump directly to EV charging. I was not sure exactly of the whole audience, so I will go a little bit from the basics until the specifics. So you know very well that electric vehicles and electric vehicle charging is not new at all. It's more than a century that electric vehicles appear, and in this battle that we have 1 century ago between DC and AC, where it was basically the same happening between the electrified transportation and the transportation based on the internal combustion engine. Here I always make the assumption, or not assumption, the specific case of the Jamaican Tant car, which was the first electric car actually to reach the 100 kilometers per hour, and it was actually a Belgian car. So I always tell if I'm giving this presentation or this part to Belgians, to be proud of that milestone in electric transportation. But we know what happened. There was no power electronics at that time. DC was not offering that much in comparison to AC, and charging times and the availability of infrastructure was not that good in comparison, of course, to the fuels company or to the gasoline companies. And yeah, basically that was the end of that first phase of electromobility. What I found quite interesting is that at that time there was also the discussion of battery charging, and actually range was not that a problem, because they were intended, these cars like this one of the Baker Electrics were intended to be used actually for towns and suburban service. So pretty much quite similar to what we have right now. If you like really this topic, I invite you to check the Baker Electric's flyers. They are quite interesting. More than 100 years ago, this is from 1910, and there you can see how these cars were advertised, and in some cases, that is not that different from what we have right now. It's quite interesting to see. But then, of course, going into the details, how in order to understand fast chargers or battery chargers or even conventional electric vehicle chargers, it's important to know what we are charging, and that's perhaps one of the conclusions that I can give right now is that sometimes we forgot, or we tend to forget what we are charging, and basically we are charging batteries, and batteries they operate and they perform in a certain way that we tend to forget. That's something that I will explain in a minute. So yeah, basically you know more of the cars that we are having right now, they follow this kind of a skateboard design where we have a big amount of batteries, and we know that batteries are becoming cheaper and cheaper, and that in a few, probably couple of years, electric cars will be cheaper than conventional internal combustion engine cars. But then the key is what is inside of those battery packs, and there we have most of the cases, and perhaps that will be the case for the upcoming decades. The mainstream case is that we will have lithium-ion batteries, where we can have several volumetric energy, gravimetric energy per cell. But basically the thing is that if we want to ride longer, or if we want to have a larger or distance to ride, we need a larger battery pack. So that's I think quite straightforward. Then we need to review or to make to remember how the charging process in a battery is conducted. In most of the cases, or that's the classical case, we have the points where the battery is charged at constant current and constant voltage. And at the beginning of the charging process, we charge at constant current, and then we start to charge at constant voltage. So that's the point. Where is this change happening? basically it depends pretty much on many conditions, and that's also another point to consider during the whole presentation, is that not all the batteries operate the same. They have a quite specific working conditions based on lifetime battery, lifetime temperature, humidity, and many other factors. But more or less, most of the, let's say, new batteries, we can tell that that point is around 80% of the state of charge of the battery. Why I am mentioning this is because also we tend to forget, or we tend to think that battery charging is conducted at constant power during the whole charging process, and that's something that in practice doesn't happen, and that is actually a point to stress in how the fast charger or the battery charger will work. So based on this, basically, if we want to make the charging fast, we have to, of course, to decrease or to reduce this time. And at the beginning, this is the time where we charge at constant current. So basically, if we want shorter charging time, we have to increase the current, and basically we have to increase the power of the charger. And that is basically the reasoning behind why we are having higher and higher powers in the charger, because basically we want to charge faster, which is quite obvious. Then we know, of course, we need larger battery packs to have a larger autonomy, and we need higher powers to charge quickly. So then we can go to the cars that we have nowadays in our cities. This is, for instance, the Tesla Model S is more or less one of the Tesla Model S types, has almost 100 kilowatt-hour battery capacity. What they promise is more than 500 kilometers of range. But then you can see here what is the time required to charge such a battery. It's a quite large battery, 100 kilowatt-hour. If you charge it with, let's say, regular level 1, we will discuss what level 1 is, charger, or a conventional, let's say, charger that you have at home, which is in the area of several kilowatts, then you will see that you need quite many hours to charge such a car. Then if you have something close to the CHAdeMO, which is 50 kilowatts, you will need 1.6 hours to charge such a car. But then if you have a 400 kilowatt infrastructure, then you will see that you need only 12 minutes to charge that car. What happened with other cars with smaller battery packs? We have these other, what I call premium cars, like the Audi e-tron or the Jaguar I-Pace, similar battery packs, and you will see similar times. Let me have a bit of water. What happened with other types of cars, smaller ones like Zoe, or the Nissan Leaf? Yeah, of course, the smaller the battery pack, of course, the shorter the time required to charge it. And finally, some others like and these plug-in hybrids or small cars with smaller battery packs. So once again, we need shorter times. What is the problem? That none of these cars can handle 400 or 350 kilowatts charging power at the moment, and that's perhaps another conclusion at this point is that, yeah, we are talking about increasing the charging infrastructure in terms of power. It's a different discussion if we talk about numbers of chargers. But if we think about chargers, fast chargers, perhaps the proper question is, are really or are our cars or can our cars that we have right nowadays can handle these 350 or 400 kilowatts that is more or less how the standard is moving. What happens if we do fast charging, and that's another part that is important to be clarified, because of course if we want to compete against the charging times of internal combustion engines, we have to do our charging within minutes, and then we are talking about fast charging. But let's imagine that we don't have a problem with our car, that our car is being able to be charged at those hundreds of kilowatts. Then still we have another limitation, and what are those? Basically, we can go through the model of a battery itself. And here I want you to remember that this is not only applicable to cars, but also the batteries that perhaps we will have at home, or the batteries that we will have, for instance, if for the DC Therese project, if we are thinking in microgrids, and if we are having storage in general, and we want that storage to charge faster, we have to remember what happens if we charge quickly those batteries. So basically, we can see that the battery has its inherent stray or parasitic components. And if you remember a few slides ago, we were talking about currents. So if we want to charge faster, we will need to increase the current. And if we increase the current, of course, we will have higher losses in these parasitic components. And the higher the losses, of course, the higher the temperature that we will have that we will have in our component. Basically, we will need to dissipate more losses in heat, and we have to handle that heat. Plus, that those are losses, so we are actually losing energy in the battery. Only charging the battery, not even, and here we are not talking about discharging the battery to the load. It's like we are losing energy in only storing energy. So what happens if the temperature is too high? Basically, batteries start to degrade, they start to lose capacity, performance, and in some cases, if they are not treated well, of course, we can have a thermal runaway, and those are the parts that we don't want, neither in a car or nor our home or our, let's say, storage facility in our microgrid. And what is the solution for that? Basically, the BMS, the battery management system, is the one that controls that. And how BMS does that? Basically, they do the thermal management. They measure constantly temperature and they predict state of charge, state of health, and different parameters. They measure, of course, electrical management, and they dictate based on a safety management how, and of course, based on a data acquisition, of course, how the charging process is conducted. So that is one of these things that I was mentioning that we tend to forget or try to think that battery charging is conducted at constant power, and that if, let's say, if Tesla comes and tell us that the new car will be charged in 5 minutes, and that's possible indeed, but only at peak power. But in reality, I would say not every single car charge at constant power during the whole charging process. Why? Because we have a BMS there, and why? Because the internal structure of the battery or the chemistry in the battery doesn't allow it, basically. And why is that important? This is the main conclusion. So basically, charging rates are determined by the battery technology, and basically by the BMS because we need to protect the battery, basically. And let me see where we have the moment. So how or what happens in practice is that, of course, we need still to charge faster, and there is a system, a BMS system, that will not allow us to charge faster, because basically our temperature is increasing inside the battery. So what we can do is basically we cool the battery down, and that is basically one of the what the manufacturer is doing. This is an e-tron, an Audi e-tron battery. And actually here I can mention that these cars, the e-tron lineup is actually manufactured here in Belgium, near Brussels. So we have the battery pack. This is the battery pack, and here you can see the BMS or the BMC is the battery management controller doing the battery management system. But more than that is that we will have a big cooling system here. So it's kind of almost required that if we are going to do fast charging, we will have to cool our batteries. And here again, this is not only applicable to cars. Again, please think in the batteries that we have at home or that we will have at home, and the batteries that we will have in our smart grids. I don't know if you ever experienced, but I experienced one of these fast charging in cell phones, in smartphones, and I think it was several years already when this fast charging is starting to be introduced, and the battery life of those smartphones was quite degraded within a few months only, and it was exactly because of this. So yes, liquid cooling is required for fast charging because we need a higher current in the system. So that's the basics, and here again the takeaway messages is let's not assume that battery charging is conducted at constant power. That fast charging is possible if we handle the temperature in a good way. That most of the cars nowadays they don't allow extremely fast charging, meaning more than 100 or in this case 100 kilowatt charging. And yeah, those perhaps are the messages to this moment. Then we can talk about the classification of chargers, and I don't know if there are any question to this moment.
I haven't seen any, but if there are any questions, it might be a good interval or break-up session to ask some questions if there are any.
Yeah.
But I haven't seen any so far. And as a reminder, if you have any questions, please feel free just to ask them during the session, preferably with the raise hand functionality, so that we are notified thereof. But otherwise, please feel free to continue.
Yeah, thank you. Perhaps this is one of the parts that is more interesting for the TC3 project, because we'll be talking about classification and perhaps a little bit about the standards of charging and how it's conducted. So how charging is conducted? Let's remember how charging is conducted at the cell level, and then we can move to how to let's say how to supply that power, and we can talk about if it is AC or DC, and what kind of conversion is required. So how is that done in practice? So it's something like this. Basically, we can have the regular AC power supply or AC grid, conventional one. So then we use a power conversion, basically. So we use a rectifier to rectify that let's see AC power and then we convert it to DC. So in the DC, usually we have an isolation, and this is the most common case. So we have a DC-DC converter with isolation, but in practice there is a DC to AC, so we go back again to AC, and we have a transformer there, a high-frequency transformer, and then we rectify again, and basically we can charge the battery in such a way. And that is exactly the same how our cell phones are being charged, and that is exactly how the batteries that you have at home will be charged. But I think in the next slide we will see other ways to charge batteries. Well, then we know that the battery management system sets the charging current and the voltage level. So basically, that is the one that tells how charging processes are conducted. And then the question is where to put all of these systems. Is it within the vehicle or is it outside the vehicle? And it will be the same discussion where to put those chargers. Again, if we are talking about homes, or again, if we are talking about storage facilities for smart grids. If we put everything inside the car, then we call, of course, that this is an onboard charger. And nowadays, the new cars, they are implementing up to 43 kilowatts chargers, onboard chargers. And then we can see already, if you remember the table some slides ago, already 43 kilowatts is quite good in terms of charging times. Then the question is how to supply that power. And then if we don't have, or if we don't use that, because of course every car will have their own onboard charger, but if we don't, if we want to charge faster, basically, we use an off-board charger, or more specifically a DC charger, which puts all of these systems outside the car, and basically it allows a faster charging. And here, at least for road transportation and for, let's say, for the automotive area, we are talking between 50 to 400 kilowatts. Then if we talk about coaches, buses, trucks, trains, and much larger transportation systems, of course, we will land in the area of megawatts charging. But basically, the process is similar. So that's at least the division between on and off-board charging, and how is defined. But it's not only like that. There is actually a wide variety of how to charge batteries. And here you can see the systems basically, and how many conversion stages they have. The blue ones are the ones that I mentioned before, and those are like the standard solutions where we have AC to DC, and sometimes most of the times I would say we have a DC-DC stage to isolate our systems. Here I can mention already that most of or typical question that sometimes rises is if we really require isolation or not, or even in any system. And I would say the answer is not completely clear. Most of us tend to think that isolation is of course good for safety purposes, but still there could be the case that we have simply this type of connection where we can have, or even like this, where we can have a low frequency transformer connected to the mains, and basically a rectifier to connect directly the battery. But again, we prioritize safety, and that's why we have, in most of the cases, isolation in a high-frequency transformer like this. And of course, we have the onboard charger, where all of these parts are moved to, or are also in the car, because that's the reality. There are some cases where these converters can be split. like for instance in the case of wireless charging, where we have a primary of the converter on the let's say on the road or in the parking lot or in the charging station, and the secondary is basically in the car. But I will not touch that much wireless charging, because that's perhaps not applicable at the moment. But the message is, if we are having billions of electric cars and we will have to charge those, and we are talking that we will reach even megawatts of charging powers, of course, material-wise, of thinking about, for instance, copper. We will have for sure a shortage of copper in the future. There is actually the comment always, if you want to invest in copper, because of course there will be, and you know, in these discussions, if we are talking about electrification of remote areas and how to electrify or areas that has no access to electricity at all, of course we will be using more and more electricity and materials for that. And there, with that discussion, wireless charging becomes a good solution, because then we cannot, if we imagine, for instance, a road where we can be in constant charging process. Of course, our batteries can be decreased, and we don't have to charge in the range of megawatts or hundreds of kilowatts, because basically we are being charged almost during the whole moment. It's like having your smartphone being connected almost all the time. So of course, you don't have that much autonomy. But so that's why we have this split here. How those can be implemented in practice, and this I like this representation from Fraunhofer. Yeah, and there is another possible conclusion that I can give at this moment is there is no a clear or a right answer on how to implement a smart grid, or how to implement let's say a battery or a charging facility, for instance, a parking lot for cars. If you have existing AC infrastructure, of course you want to make use of that infrastructure. If you don't have any infrastructure at all, perhaps you can consider implementing DC grids, like the discussion that you had with George, and so on. So it's pretty much dependent on the specific conditions of the project. But then, of course, if you have a low voltage these AC grids, you can use conventional low power charging. You can also use with the same grid fast charging or DC charging. This is by DC charging or high power charging, and there you can see already the difference between the plugs. Also, if you have medium voltage and you want to connect directly to the medium voltage, I remember there are some interesting studies of how to charge cars directly to the medium voltage mains using solid-state transformers and yeah, more use of power electronics, not only having like a low frequency transformer, a big bulky one, thinking again in the use of materials, iron and copper, and then if we replace this low frequency transformer by a high frequency transformer here, much more compact and perhaps more efficient, then there is also a possibility to not directly have like a low voltage distribution grid, but rather to connect directly to the medium voltage. And more with the concept of smart grids and storage. If we have a storage somewhere else, of course you have the possibility to have a dedicated low voltage microgrid or nanogrid, like the one that George presented or the one that we have at Energy Bill. So why not? to have those kind of examples. And then this is the one that I was mentioning before, is the inductive or wireless way of connecting yeah, to charge batteries there. Here I would like to mention two examples from Hitachi ABB. They were having this project called Emotion, where they were charging a certain amount of buses, and they were using yeah, different strategies. One of these is the conventional AC, where they, of course, they have the AC distribution, and based on that, they power many DC chargers, basically. But all of those, the DC chargers are connected to the AC side. But also the possibility of having a DC grid. So it's the same case of having the AC, the main AC, let's say transmission or even distribution side. But then we have let's say rectification at the very beginning of this step, and we have the kind of distribution in DC. And there is also the possibility to have a storage, a big amount of energy stored and somewhere else, and based on that we can power our chargers. And here all of those are not connected to AC, but connected to the DC mains here. Question is, and it's exactly the same question about DC microgrids. What are the suitable voltages? And here again, it's I would say there is not a right answer. At least in this case, the E-mode they were using, or the Emotion project, they were using, to my understanding, voltages around 1 kilovolt or 800 to 1 kilovolt. Yeah, DC transmission voltages or DC distribution voltages. Sorry. It depends pretty much on what you want to do. Let's say if you are implementing a certain how can I say it, certain prototypes or certain demonstrators or of smart grids or microgrids. Let's think, for instance, in South Africa, it depends pretty much on your loads. How many cars would you like to supply, or if it's just a storage to supply the or to be a backup of the microgrid. Then based on that, it will be easier to calculate what is the suitable strategy. But then telling that 1 kilovolt or 800 volts is the best solution for every project, I think is not the case. So yeah, that basically is the conclusion at this point. There is no best solution as such. It depends pretty much on the conditions and what is available in terms of infrastructure. So those are the cases of how to connect chargers, or how to supply power to the chargers. Also that dictates or that determines the power levels that you will have per charger. But then it's also quite known that we have levels of charging, that we have also modes of charging, and it's quite, let's say, it's not clear what is level 1, what is level 2, if it is the same of mode 1 or mode 2. You can see here the example of what is AC 1, 2, and of course the DC charging. DC charging or DC fast charging by default is the easiest in terms of let's say standardization, because it's basically higher power than the one that we can supply by the AC grid, and basically it starts already, I would say, higher than the power that we can supply with the onboard charger. And onboard chargers, as I mentioned, most of the cars, they can handle 7 kilowatts, 11 kilowatts in the onboard chargers, but since I think 2019 or last year, we have already cars with 43 kilowatts onboard charger. So if we are talking about fast charging or DC charging, of course, it will be something higher than that. So in the range of tens of kilowatts to hundreds of kilowatts, at least for automotive. But then this is levels. There is also, I was mentioning this, there is also the classification of modes. And here is pretty much the same. Mode 1 is quite similar to level 1 in the range of several kilowatts. Mode 2 is already reaching tens of kilowatts, and mode 3 is this case that I mentioned of 43 kilowatts, and that couple of cars they are already offering that. And mode 4 or DC charging intended for off-board, they are already targeting hundreds of kilowatts, as we will see. So what is, yeah?
Apologies, maybe a question in between from my side. I do see in the Netherlands, but it might be that it is happening elsewhere as well, developments of low-speed DC charging situations where you can go between 10 or 20 kilowatts of charging. Mm-hmm. What level or mode would they then fall under? As they, I think, would be considered off-board charging, but with lots of less power. Is that a difficulty in this structure, or not?
That's exactly what I was about to say. That basically it's just no, it's not it's pretty much a definition. So it depends pretty much on the association that will define certain numbers. Let's say if it is a SAE or if it is a IEC or if it is a GTB from China. That's basically definition. But at least, let's say, talking about the case that you mentioned, if it is, if you are basically using an external device and you are not using the onboard charger, then of course it's DC charging. And nowadays we have a mix of concepts on what is a fast charger, an ultra fast charger, and a flash charger. And there is let's say, a misunderstanding of what exactly fast charging means. So I would say if you are charging at 20 kilowatt, 10 kilowatts in DC, and you are using an external device, of course that's off-board DC charging. So that's at least the point is which standard will you follow also. And here perhaps I would like to let me jump to where was it? I think I didn't have it. There is let me see, because I had one interesting figure. I don't know if I deleted it. Where was it? Well, but it will come in the following slides. That basically, what happens in practice is that we have a charger, and outside of the hardware is the same. Probably the communication is a little bit different. And outside the charger, we will have the plug or the connector for the HDMI one, for the CCS one, or for the whatever new standard will come. But at least the hardware is the same. So I would say don't worry too much if it is 20 kilowatts and it doesn't fit with the certain standard, because the hardware inside is pretty much the same, only offering the possibility to charge with 2 or 3 different plugs. That's did I answer your question, or was it something different?
Yes. No. This was exactly. There's, as you were saying, there's lots of interest and awareness to upping, so to making higher charging speeds possible. especially for highway, expressway applications for trucks. It's very usable, but I can imagine at some stage, also for residential purposes, if you've got PV attached to your house or close to your house, maybe you already have electrical storage, battery storage in or around your home, then it might be considered more and more interesting to also go to DC charging, as you have a sort of DC bus already.
Indeed, exactly. Yeah, if you have the possibilities, and we know already the advantages of DC, and if you have the possibility to have at least some, even if it's a really small DC distribution grid, even if it's at low voltage, why not making use of that and connecting it directly to your charger, and there you will skip some stages of AC to DC conversion. So it makes a lot of sense from the point of view of efficiency and even cost. And if we think in all the DC loads that we have at home or that we have in buildings or even in districts, I think that makes even more sense. Yeah.
Well, thank you. Please proceed, or maybe it might be, as we're already an hour on the way, it might be good for a small break if you're up to that already, or I'm not sure. I'm not timing you. I'm not trying to stress in any way. If you feel you're up to an extra 15 minutes or something, then we can do a quick break later on. But if you say, well, it might be a good time now.
Well, I was mentioning that I was preparing this for 90 minutes, and I am thinking that I am quite really late. So yeah, I would say let's proceed further.
Okay.
If you are not that tired.
No objection from my side. So I'm happy with that.
Yeah, and yeah,
Please.
let's see where we have until what we. The meeting is up to
the meeting
3:30, is it?
3:30, yeah. So there should be plenty of time.
Okay.
And I am also available afterwards if that is required. So that's possible. Please take your time, and if need be, we'll look at the timing slightly. But please tell the story as you want to tell it, to share it with us.
Yeah. Okay. So the point is, yes, there are many standards and even probably more to come. Just to give you an idea of those, this is, for instance, the SAE from SAE, but this is already 2009. How level 1 is being set, and this perhaps the most used nowadays, because it's like we connect to a low power site. What about level 2, which is also connected to the AC site, and there is, of course, a discussion of communication and power. But just to give you an idea of how those let's say standards differ, this is, I'm not mistaken, level 3. Also, well, talking about DC charging, already there, what we mentioned, and these ones from the IEC, so pretty much the same, perhaps more emphasis in the safety and so on, but at least we consider that the charger will be able to handle those powers. So the definitions are really additional information. At the end, what happens is that we are using certain hardware to charge what the BMS needs, basically. This is the case of I will not spend too much time on this, the AC6219, and so on, quite many others regarding DC charging. So perhaps if you're interested, you're more than, let's say, invited to go into it. But yeah, the message is how we are using the hardware to charge our batteries. This is another case, but again, I will not jump into this. What I would stress here is that what we have, at least from the CHAdeMO and that is like the Japanese standard Actually, this is the one that we have at Energyville at the moment. CHAdeMO 1.0, if I'm not mistaken, and also the CCS, which should be becoming more and more used. And then what I was mentioning before, we have a mix of terms: fast charger, ultra fast charger, extremely fast charger, flash chargers, and so on. And what is true is basically what are the powers that we are charging at, and basically what is the maximum power that our infrastructure can provide, or the standard that can provide. We can talk about a fast charging, at least in my presentation I am using fast charger as a whole. For let's say heavy duty cars or buses or trucks, when they start to talk about 400 or 350, it's already intended for that. Why? Because as I mentioned before, not many cars at the moment are able to handle those powers. And this is actually the picture that I was looking for a few minutes ago. This is what happens in a charger. Yeah, standards like CHAdeMO, CCS, or GBT from China. They differ in the cable connector, in the communication protocol, in the safety procedures, as we saw in the previous slides. Even they already, some of them, they already consider the vehicle to grid features, where we can, and that's quite interesting, of course, for microgrids, where we can give power back to the grid. But what happens is that at the end they use the same power converter hardware, and this is actually the case that we will see, is that we have the CHAdeMO connector, the CCS connector, or any other connectors outside of a charger. So yeah, coming back to the question of the 20 kilowatt DC charger. And if there is any concern about standards, I would say there is none, as far as most of them they are considered. So it will be, probably we will jump from the era where we have to select if we pump diesel or gasoline 95 or 98. Towards the era where we have to select a CHAdeMO or a CCS or GBT chargers, and that's the change that we will experience in the future, or even nowadays. Future is now. I was mentioning in this case that most of the cars, they cannot handle 350 kilowatts, but still we are already seeing some new cars, like this is a Porsche Taycan, quite let's say important, because it puts the milestone of cars with 800 volts of 800 volt battery and 800 volt powertrain, and is becoming the standard for upcoming cars. And all of those, or well, the majority of those, at least the premium segment, will be able to charge with this CCS 350. So it's not only, and this CCS 350 is basically the 350 kilowatts. So 350 kilowatts and 450 kilowatts will not only be dedicated for heavy-duty cars, buses, and trucks, but also for automotives or for let's say road transportation for our cars. Yeah, that's the very same conclusion, that premium EV charging technology will reduce charging times, also for the standard segments. And here is again the discussion of what challenges are raised at 400 kilowatts, and we are talking more and more about hundreds of kilowatts. But once again, we tend to forget what really means to have hundreds of amps, of amperes flowing in our conductors. And what is happening actually is that the connectors will become, or are becoming, quite heavy, and they are also in need of cooling, because we will be transporting even yeah, almost half or more than half a kiloamp through these wires, and again the losses are quite high, and they become they will be translated into heat, and we need to dissipate that heat in some way, and because of that we need also to cool those cables down. So what will happen? We will end up with very heavy connectors, and at some point that will become also an issue. Yeah, that's the conclusion. Thermal stresses imposes quite many limitations. Even then, we are now already talking about assisted charging, where basically we will have like a kind of a robot connecting those chargers, because basically a normal human we cannot lift or will not be able to lift those cables because they will be quite heavy. Then it's talking about buses, trucks, and so on. Of course, we have in the case of pantograph where we can charge. This is the case of already 1 megawatt. And the point that I mentioned before, we can, let's say, if we are electrifying more and more, perhaps we will see the case where we are having wireless charging also to avoid this kind of issues. So that's what I wanted to say regarding, let's say, the types of charging. What happens when we are charging our cars at different powers. But then I would like to go a little bit in detail of what happened inside the charger when we are doing that charging process. And there I would like also to keep in mind the question again of what happens if we are going to charge at 10 kilowatts or 20 kilowatts in a DC charger, because in practice that's happening a lot, I would say. So yeah, this is the fast charging part. I will not spend too much time into the electronics, but those are the type of converters that we will see at the side of the rectifier, and these are the type of converters that we'll see at the DC-DC conversion part. Yeah, those are consolidated and well-studied topologies and are the ones that are being used nowadays. But yeah, high frequency transformers, as I mentioned. So this is the CSCS 350, let's call it a standard, where we can go from a wide variety of voltages. For instance, some cars of Toyota, they use a 200 volt battery. Quite many, they use a 400 volt battery, and as we saw, more and more cars are using nowadays 800 volts battery packs. So depending on the level of current, we will be charging in a slow manner or a quite fast way. So this is more or less the operating area of where these converters or where these chargers will be working in. And basically, if we are going to charge a wide segment of cars, our hardware need to work in this wide variety of powers, let's say. What happened well, it will be in different powers indeed. What happened in practice, and this is actual real data, this is one of the most interesting parts, and in my opinion, at least talking about inside the cars. Again, the conclusion, this is real data of charging profiles of real batteries of certain cars. What happened in practice is that none of them that are conducted at constant power, what I mentioned at the very beginning. And why is that important? Because basically we will be moving a lot during this window, and that's part. And that's a challenge that we have seen, at least for the converter part, that keeping efficiency, if our charger needs to work in a wide range of points, it's a challenge. At least talking about for the converter itself, for the charger. This is, for instance, information of an Audi e-tron. This is the charging profile of the Audi e-tron design. Would be the ideal conditions, but we know already that there is no such a case. So basically, if we want to charge an Audi e-tron, our charger will work in this area. What happened with these three that I mentioned before, like the Jaguar I-Pace, the Kia Niro, or the Hyundai Kona, we will need another range. And this is even more interesting. This is also real data captured by a Tesla of how charging process is being conducted. And here, and that's why I mentioned in the question again of the 20 kilowatts or 10 kilowatts, because that is actually happening in reality. Even for a Tesla that needs to be charged, or that the maximum power is around 100 kilowatts, what happens in practice is that they start to charge or to increase the power rapidly, but then this is a rather, let's say, not new battery. This is not a new Tesla, but already with some years. And what happens in practice is that the charging profile is not constant at all. It's actually decreasing by the time that the battery is being charged. And there will be a case that even having a 350 kilowatt charger connecting charging a Tesla, which is able to charge at hundreds of kilowatts, that the Tesla will be charged in the area of 30, 20, or even 10 kilowatts, and that will happen. So that's another point to consider when you are designing a microgrid, that to not assume that all your chargers, if you design a charger, let's say for 50 kilowatts or 20 kilowatts, like the case in the Netherlands, that assuming that your charger will be working at that power during the whole time, because that will not be the case. Neither for the batteries at home, neither nor for the batteries as a backup of a microgrid. So that will be the area of operating range of a charging in this kind of Tesla. But then I mentioned this like the Porsche Taycan, that is 800 volts. So if we also intend to charge this car, we will need a larger operation in our converter, in our charger, basically. So what it's one of the possibilities is to use a modular approach, and that is actually being used at the moment. So instead of having one single piece of hardware, one single converter that can charge one Taycan, for instance, and we can have several modules, for instance. We can have two stations of 175 kilowatts each, and they can charge also a Taycan, but they can also charge two e-trons, for instance. In this one, we will not be able to charge perhaps two cars at the same time, because there is only one converter. So what happens in practice is that we will have modules. We will have a modular design, and basically give us quite a large or a high flexibility in our processes. And this is what is happening. Indeed, we are charging, we are having several modules with the ability to charge several cars. And if we think in the case of those charging profiles, of course, we will not be using the whole power of each of those. So we can make use of that technique to use something like in this case. Well, this is for let's say reliability purpose. Also, if one module fails, of course we can have the others. But also we can increase the efficiency with this kind of let's say module shading, where we can, if we are in the low power charging this Tesla, for instance, we will only use few modules and not the whole charger. Let me see my slides. This perhaps is
Sorry,
also important. Yeah.
there's a question from George in this particular
Yes.
regard.
Yeah.
A small question. In one of the first slides of the presentation, you showed some or a table with the charging times for different charger power ratings, actually.
Yeah.
And I remember from the 400 kilowatt charging rate, together with a 100 kilowatt hours battery, the charging rate would be around 12 minutes. So that would assume that you charge at more than 400 kilowatts, because otherwise it should be like 15 minutes. But then also the question popped up when I saw one of the slide 33, where you showed the charging rate that it even was not constant. So maybe if you have a 400 kilowatt charger, the total power you will deliver averaged out over those 15 minutes will maybe only be like half of it. So how do we get to that charging time then?
That's a good question indeed. Let me see it back. So indeed, we have 12 minutes for the 400 kilowatts in terms of 100 kilowatts. Yes. So perhaps it's also a mistake from us of the calculation. But let's say in practice, and that's the point that I wanted to stress, is that yes, let's say manufacturers or OEMs, they will tell us this car can be charged within 5 minutes, or if we do the calculation, yes, it will be 15 minutes. But in practice, if we consider and all of those are actually based on new batteries, and thinking only like a fast constant power. If you have a new car, probably that will be the near the case, and as most of the let's say the cars, new cars, or in order to protect the battery, they will not reach 100% state of charge. Although they show you that information, and in the also the same with cell phones, they will tell you your battery is at 100%, but to protect the battery, actually they are at 95 or even less. So that's something that that we have to consider there. That it could be 15 minutes indeed if we make the right calculation. But in practice could be something else. Indeed. Yeah.
So it's basically the same as with other cars, where they give the fuel consumption in liters per 100 kilometers.
Exactly.
But it's never achievable.
Yeah, and that's exactly the same discussion of autonomy. They will tell you this car is 500, 400 kilometers, but they were tested with, let's say that these driving cycles, like well, the new European driving cycle is not used anymore, but this kind of standardized cycles. And when you go and check the reality, well, those cycles are not, let's say, near the reality. Of course, it's a good way to compare cars because it needs to be a fair weight, so it's an standard. But how close are those to the reality? It's perhaps not the case. So yeah, coming back to your question, yeah, our bad that the calculation perhaps is not correct, but more than that is that the concept of time that in practice will be longer, and depending on the conditions. Let's say it will not be the same charge in a car in Helsinki or Stockholm or Reykjavik that charging it in Cairo or so. So that's pretty much depending on the conditions.
Thank you.
Okay. Let me go back to the point of chargers. Well, perhaps I will go a little bit faster, at least to try to cover all of the points. I was mentioning the modularity, so yeah, we can have an onboard charger, which is a module, a single module of up to 43 kilowatts. But we can use the modular case to charge small cars, premium cars, or even larger vehicles like this one. And in practice, what happens is that all of those they will use a modular design. So again, if you are designing a microgrid and you are considering charging batteries for any application, perhaps you will end up in going for modularity in that respect, either if you are going to charge really kilowatts or megawatts. Yeah, so different target powers, different number of modules. And if you go for the range of tens, hundreds, or even megawatts, perhaps what it will be changed is the number of modules rather than or perhaps the power per module. If you look, for instance, what a Tesla looked like, is like this. They have quite many modules there with several rated powers. This is also interesting to see. Well, this is pretty much the same, and these are some companies developing chargers, and there you can see some output powers per module. Some of them are not known at the moment to us, but they are in the range of tens of kilowatts. So even if we are talking about hundreds of them, the commercial solutions are following the modular approach, and all of those are in the range of tens of kilowatts. Yeah, so perhaps something to mention here regarding our internal project. I will jump to this one. This is the parts where we are considering this wider window of operation. We are trying to optimize. This is actually the prototype, but the idea is to improve it further to optimize this. Let's say to maximize the efficiency during most of the points of the charging process. How can we do that? First, optimizing or selecting properly the power per module, and then also targeting the efficiency of each module. And we have noticed that most of the challenges lie on the magnetics and the semiconductors, and how they affect each other. And basically, that's one of the main objective of this project, and we hope to present you some results soon about it, specifically talking about the magnetics of these chargers.
Please, Wilmar, don't rush, because it's too interesting. So take your time, please. Normally we can proceed till 4 o'clock.
Okay. Yeah, perhaps I will not take that much. We'll just give a few words about infrastructure. I am not a power system person, but still there are some interesting information that perhaps you can find it interesting, talking specifically for the DC Terrace project, for instance. Yeah, what is the fast charger manufacturers, how they work, and what is the trend and the impact towards the grid. I think this was last year that we did this search of charging fast charger manufacturers, and we found several companies in the US, actually in the Netherlands, also in India, France, and so on, and quite several. And there we saw quite interesting powers, and here I would like to stress out that again there is not a right answer regarding powers or to be implemented in let's say in our cities or in our projects. it depends pretty much on your conditions. If you have, again, an AC grid available, and if you need to charge a few cars, perhaps it's not a good idea to go really to the megawatts or hundreds of kilowatts of range. But still, what we found quite interesting is that all of them, they use a modular approach, so that you can also look into that to see what are your needs and how many modules do you need, and based on that to of course to design your own system. Powers were in the very same range that we mentioned, between 10 to more or less 50 kilowatts per module, depending again on the specific or types of vehicles that you will charge, or the number of batteries that you want to charge in your district, or the storage facility that you have in your microgrid. And there you can see the case of this wide variety of voltages. Yeah, this is pretty much the charging networks that we are having, and here I would like to stress out Ionity. I took this one actually from the Ionity website, and they are having quite many, let's say, activities in Europe, installing chargers. They don't do the hardware, but they install them and they operate them, and there you can see already quite, let's say, the coverage in Europe. Again, this is not the only company, but it's one of them perhaps that is having more charging points in Europe, and they already mentioned that the challenge in, for instance, in highways, and basically the challenge of having fast charging or ultra fast charging, if I call it, meaning charging in the range of hundreds of kilowatts. Perhaps it's too soon to have those, but eventually I think they will pop up more and more in our cities. Then, yeah, perhaps this is the right point to compare this. The following slides shows this study from McKinsey. I think it was 2 years ago or something, but it's still quite interesting to see that how predictions are made. If you see, for instance, all of the predictions and roadmaps and yeah, of the phase out of cars, and how many electric cars we will have in the future, and how many chargers we will have, I think it's quite difficult to predict. But still, having some numbers, I think is interesting. And here you can see that the comparison, at least, of cars. We know that we will have quite many electric cars in the future and in the coming years. For instance, here in Belgium, I think it was last week that we have the news that all of the company cars should be electric by 2026. This is practically now, and we saw all of these targets of 2030, 2050. So yeah, this is nothing new, that cars will be here, and we need to prepare for that. This is something similar to what George was mentioning. Yeah, if we have a car with a certain, let's say, battery pack, these ones are the so-called standard segment, and this one are the so-called, let's say, premium segment, like Tesla or the Porsche Taycan, and all of these they consider charging of 15 minutes. So it's clear that if we need or if we want to charge our cars faster, we will need higher powers in our streets. But what about those predictions? So again, coming back to this study, we don't see that many, let's say, and this is quite related also to the study, or the statistics of Ionity. we don't have that many fast chargers, and by fast chargers, hundreds of kilowatts a charger nowadays. And I think in the future that will be also the case, that we will not have that many. So level 1 and level 2, perhaps level 3 or mode 3 will continue to be the main charging, let's say, type in the next decades, but still we will see more and more fast chargers. It's not easy to install a 400 kilowatt charger. Basically, we need to think in the infrastructure behind it. It's much easier to install 10 kilowatts, 7 kilowatt, 20 kilowatt chargers, because they can be installed at home. Of course, they need a dedicated infrastructure at home, but still it's much easier than installing megawatt range chargers. So that's basically the conclusion here. Yeah, we need to prepare for fast chargers, but they will not be here that's fast. Let me see the coming one, perhaps not that. This perhaps is interesting to see, and that is the constant question, like will our existing grid will handle the upcoming amount of electric cars? And the answer, the short answer is yes. We don't see, and more studies, they don't see a bigger concern in terms of installed capacity, let's say. As you can see, this is the case of the consumption in 2015, 2030, and you can see the portion dedicated for road transportation. I mean, this is electricity, of course, for electric cars. So we don't see a big change, of course, because as you saw from the previous slides, charging will not be conducted really at that amount of kilowatts that we saw. They will be again, level 1, level 2 will be the mainstream, or will be continue being the mainstream charging type. But still, if we this is interesting based on the study of the battery, the electric cars in Germany, and how they predict the let's say the adoption of electric cars in the market, but still we don't see a big issue for the grid. The problem, and that is the main issue, is the peak power. Why? Because we are basically social animals, and we tend to do basically the same. So we go back home nowadays and we use a lot of electricity. Perhaps we will be charging our cars at home at night, and there is actually the issue. We will perhaps have an increase in the peak power at those, let's say, at those dedicated hours. And here again in the study, they were predicting those cases where if we have an average electric vehicle demand, we will have an increase in the peak. This is even more predicted here. But then the answer is microgrids, of course, and if we have storage, and if we have more renewables and so on. But again, this is perhaps out of the scope of the technology. Then we will handle that for sure. I took a figure from Hitachi ABB, and that's, I think is a quite nice representation of what will happen in the future. Nowadays we are charging a lot at home, but more and more we will see more chargers at work and more chargers in the public, in our public areas. Let's say cities are not that fan of having more and more chargers, but still that will happen. And then we will see that basically the trend will change. We will pass from charging fully at home to start charging more at work. It's the case, for instance, at Energiville. We can charge at Energiville, and I think if we have the option to charge at our work, perhaps not paying that much, versus charging at home and reducing the capacity that we can use at home. Well, basically, we will be using more and more the charging facilities at our work and in the public area. So that will happen. We will see that not all the electric cars will be charged at night. We will be seeing like a more distribution of the charging, and the designers of the microgrids have to take that into account. It's also a complex issue. It's not only regarding technology, it's also about regulation and how the cities and governments see that. But at least the message is that we don't see really a big challenge towards the installed capacity, but rather towards the peak and the peak shaving, let's say, strategies that we have. And with that, I would like to finish going back to the project of a Smart Door, where we were having this, let's say, a smart charging, where even at work, or even can be also be implemented at, let's say, in districts. If we are at home and we know more or less how to prioritize charging of certain cars. Let's imagine our neighborhood, and if we have hundreds of homes, and all of those they have an electric car, that there is somehow a strategy driven by the microgrid designer to charge cars in a smart way, that they can be charged at different hours. I think that could be really a good strategy of how to deal with the peaks that we will generate. There was, for instance, the case at the energy bill, where we were thinking how to, let's say, synchronize electric vehicle charging with the agendas of each worker, of each staff, where we can tell we will go out of the building at 5 or 3 or 1, or let's say 1 hour after we enter the building or something like that, and therefore we can more or less prioritize certain cars over the others. But then there are more things to consider, like what will happen with data protection, personal data, and so on. So it's not an easy task, I would say. So that's pretty much what I wanted to mention, to use perhaps some practical consideration, and perhaps give away messages to you, and in general, not only of course to the audiences. If we think about installations of battery chargers, we don't have to consider only what is behind the charger, but also what is inside the charger. Again, there is no best or better architecture. I cannot tell you use a DC distribution system at 800 volts, because basically I don't know what will you charge with that. It pretty much goes to the to every project in particular. So basically you will have your own customized architecture. Yeah, what I mentioned, battery chargers will not raise that many challenges to the grid as many think. Peak shaving needs to be there. It's not only about the grid, but also about the hardware. As I mentioned, efficiency inside the chargers is quite important, and I think most of the works are only focusing on how many chargers do we need, where to place them, but sometimes we forget that we are charging batteries, and that charging batteries is not easy and is not constant, in a way that charging a battery here is not the same charging battery somewhere else, and that one car is not the same as others. So, and yeah, massive electric vehicle adoption will rapidly increase the demand, but is more the peak load. And based on the experiences of this Smart Door project, I believe that smart charging is the answer to deal, among other strategies like using backup solutions, storage, use of renewable energies, even hydrogen could be also a solution. So we need to have a mix in order to do this in a smart way. So yeah, that's pretty much what I wanted to say regarding fast chargers. My apologies if I didn't cover the topics that you expected, but again, this is a quite a big, let's say, word in a sense that it covers quite a multidisciplinary area. So yeah, thanks.
I think thank you very much for all your efforts, for sharing all your insights and experience from all the research projects that you've been involved in. I can imagine there might be a few questions, although it's been 2 hours. So for me as a non-electrical engineer, I was really appreciating that with each new slide you were adding more complexity to the presentation. That made it for me really good to follow on, although I can't really work on all the details. But for the other people in the meeting, please unmute yourself if you've got any questions or comments that you would like to make. Aniek, maybe to start with.
Yeah, I think it was a good presentation. Like you said, it was first started with the easy stuff and then more the difficult stuff. But for people who are not involved in the research and so, we could very good follow what you wanted to explain to us, and yeah, and making your points at the end. Yeah, it was for me very interesting.
I see a comment from Gert Jonker in the chat. He really appreciates your contribution for today. Maybe from one of the others, possibly Peter Ferreira. Yes, yeah, there you are.
I'm struggling to unmute. It refuses. Thanks very much for that, Wilmar. It was interesting. I think that for less industrialized countries like South Africa, the challenge of the power provision for electric vehicles is going to be massive. There are many areas where there is only 1.5 kVA allocated per house as the average demand, and it's going to be very interesting. And I wonder, as the car manufacturers switch to electric cars, who will be supplying the petrol cars still? Because I cannot see that South Africa will be ready for large-scale implementation of electric cars in any form for another 20 or 30 years. The electricity system is already creaking. So it's very interesting. And the funding available for microgrids would likely only be private at the moment. Yeah. So that's some interesting challenges ahead. Thank you very much for your discussion.
Yeah. Maybe something to comment there is that indeed it's a good news that we will have this phase out, but of course it raises quite many concerns. Although perhaps R&D efforts will not continue in the internal combustion engines, that doesn't mean that completely from 2030 we will not have any internal combustion engines anymore. So they will stay for a few decades, I predict, and there I see more opportunities actually for the. I was mentioned at the very beginning. I'm Colombian, and we face also quite a lot of issues in Colombia in terms of electrification. But there is also opportunities to see, for instance, implementation of DC grids. If we don't have already some existing solutions, so why not going directly to new promising strategies? And once we have such, let's say, optimized structures or architectures, I think it will be easier not really easy, but easier to implement charging of cars. Yeah.
Thank you, Wilmar.
Okay. Thank you very much, Peter, for your questions here. And maybe from any of the other participants, any other questions or comments? Maybe from Jacco, or from Peter Ehlers, or from Jacques, perhaps, or from Albert. Please feel free to share any comments or thoughts that you might have at the moment. But then, sorry, Jacques? I don't know from your side. Yes, sorry.
It was a well presented topic, and there's not much questions to ask. It was well done. Thanks.
Yes, it was well presented from my side. I can just tell George, usually it's not good to drive your car until your petrol is completely finished. So it might be something there in the charging time.
The emergency part.
I noticed that the calculation maybe was for a total charging of 80% of the battery capacity. Then the 12 minutes were okay, but then still the averaged charging rate was not taken into account, I think, in the calculation.
Yeah, usually that's the point, actually, 80%, at least to size the infrastructure is on. Yeah.
The point I want to make is perhaps it would not be wise to drive the battery completely empty, as you could see also the charging time, the initial charging time also takes considerable time. Yeah. But nothing serious. Thank you very much. It was very interesting.
You're welcome.
Thank you very much, Peter. If there are no further final comments or thoughts, then I would like to thank Wilmar Martinez again for all your efforts and the time that you've spent in preparing the presentation and then giving it to us as well. I will now end the recording, so I will